Hello again. This is the 10th video in a series on unit circle trig. And we've come to something called reference angles, a topic that confuses young math students sometimes. And I'm going to give as clear a description of them as I can, because they're very, very useful, and they can fit very nicely into your understanding of how trig works. So I'd like to start by having all of us think about a rather random problem. Let's find the sine values of all of these sort of random looking values, and I'll use the calculator. So the sine of 40 degrees. Sine of 40 degrees. Put that in, I get 0.643 rounded. So I'll even write out the decimals. It's 0.6427876. Goes on further, but that's enough of that. Let's now find the sine of 140. And I'm just going to show you. Let's see about the sine of 220. Notice it's negative, but it's the same number. And then the sine of 320 was the other one. Oh my gosh, something's going on. The sines of each of these are identical, except the last two are negative values. Huh? What's going on here? Why did that happen? The short answer is reference angles happened. I want us to look at the geometry of this so that we can figure out what I'm talking about. I've said this a couple times, I'm going to keep saying it. Anytime you want to figure out something in trigonometry that you don't understand, your very first step should be to think about how what you're doing relates to the unit circle and the angles that you're talking about. And if you do that, most of the time, the answer becomes clear. Unit circle is a beautiful thing because it explains everything so clearly. So I'm going to draw the unit circle here. And I'm going to draw each of these angles in standard position, and I'm going to be a little careful about the angles and how I draw them, and try to make them semi-accurate. 40 degrees is right here. I'm going to make the 40 right there, but it's really this angle that's 40 degrees. Now let's think about, and I'll say the sine of 40, I do want to think before I do it, the sine of 40 is this height. It's a y value. That height is the sine of 40. So I'm drawing it in, and I'm going to put it in a different color, actually. Let's make it red. So that red is the sine value. There's also an x value, which should be the cosine, but we can look at that later. I'm thinking about the y value. So that's what that 0.64 is, and it makes sense. It's a little taller than, maybe halfway up, whatever. Okay, sine of 140. I'd like you to notice where 140 is. Now, 140 is a positive rotation. It goes past 90 and 50 degrees further on. But I'd like you to notice that when I draw it in for 140, that means that this 140 degrees here is actually 40 degrees short of 180. So I hope you see that this little angle right here, since that's 140 and the whole thing would be 180, there's 40 left over here. And this terminal ray for the 140 degree angle one is making the exact same angle with the x-axis as this 40 degree one did. Notice these two markings. I've made these identical because they actually are. These are the same literal angle measures. You didn't notice it when you saw these two numbers because it doesn't look like 40 and 140 are the same. They aren't. But it turns out that they make the same angle with the x-axis, which means geometrically they're reflections of each other. I'm not perfect at drawing things, but I hope I've captured something here. These are reflections of each other and so, across the y-axis. And so do you see it? Since this one is exactly the same angle with the x-axis as that one, do you see that physically this height is going to be identical to this one? This one looks a little bigger because I didn't draw it as well. But still, do you see these are going to be exactly the same? And that is why this number was the same. Because the sine of 140 is a y value. It's the height. Now let's think about sine of 220. 220 is 90, 180. I've got to go 40 more. But notice it's 40 more. Oh, look at this. My 220-degree angle, it wasn't obvious from the number, but when I actually look at it geometrically, I realize, oh, that 40-degree angle is happening again. And I can see, oh wait, these angles are the same. So they're reflections of each other also, which makes good geometric sense in saying, oh, this little height's going to be the same as this one, which was the same as this one. And think about the sine of 220. The sine of 220, the sine of it is the y value. The y value is this thing. So do you see the y value is going to be exactly the same distance? But do you see why it's negative? It's because it's below the x-axis. Of course it's a negative number. Oh, that one's that one. And do you see what's going to happen with the 320? It's going to be the same. 320 is all the way around 270, another 50 more, which means it's going to be 40 short of 360. That's 40 short of 360, which means it's going to make a 40-degree angle there. And of course, this is a reflection of this. It's also a reflection of this. I dropped my marker. This is going to be the same. This should be the same spot. This is going to be the same. And of course, the y value is going to be the same number, except in negative because it's below. So, here's the thing. All four of these angles really have the same sine values, barring pluses or minuses, because the angles that they make with the x-axis, angles they make with the x-axis are the same. In general, if you have two angles that make the same angle with the x-axis, forget about 40, just pick something else, like maybe that angle. If you had that angle, and maybe it's going this direction, and you had some other angle that maybe is going to be this angle, there. If they make the exact same angle here and here with the x-axis, then these are reflections of each other. And they're going to have exactly the same heights. They're also going to have, if you think about it, the exact same widths too, which are the same x values, barring a plus or minus. This will be negative, this will be positive, but they'll be the same number, which means the cosines, which are the x values, will be the same, except there'll be plus or minus differences. So it bears defining a way to say what these things are in a firm definition, so that we know when we're looking at two angles that have this quality of being reflections in some way, so that their sines and cosines actually are the same number, barring a plus or minus. And that's what a reference angle is. Definition. We're going to define the reference angle for any angle we have to be the angle that your angle makes with the x-axis. So I'm going to draw this picture one more time. This is the important picture. You're going to have a unit circle, always the most important thing, and we're going to draw some angle. I'm not going to make it in the first quadrant. It can be in the second. It could be anywhere. But for any angle that you have, call this thing. We're going to define the reference angle to be the acute angle, the one that's less than 90, that this terminal ray makes with the x-axis. That angle. So, for any angle theta, in standard position, the angle, and I need to give a different letter for it because it's not going to be, it's going to be related to theta, but it's going to be different. I'm going to give it a different Greek letter. That's traditional, sorry. I'm going to make it alpha. Alpha is a relatively simple one to draw. It looks kind of like a fish. So the angle alpha, that is the acute positive angle formed by the terminal ray and the x-axis, terminal ray of theta, and the x-axis. So for any angle theta in standard position, the angle alpha, that is the acute positive angle, so here's alpha, formed by the terminal ray and the x-axis, is called the reference angle for theta. It's called the reference angle for theta. And here's the big idea. Big idea is we note that if theta 1 and theta 2, two different angles, like 40 and 140, let's say, if they have the same reference angle, alpha, because in fact that was true for 40 and 140, we realized. If they do, then the sine of theta 1 is equal to the sine of theta 2, or it's either that or they're opposites. The sine of theta 1 is equal to the opposite of the sine of theta 2. And it turns out that's a really useful thing. And it's true not just for the sine, it's also true for the cosine and the tangent and the cosecant and all the other ones. It's true for all of them. So we're going to use this note eventually. But right now, I'd like to just concentrate not on using it, but on filling out your understanding of this definition. So let's actually find the reference angle for a few of these angles, and then we'll be able to move on to another video where I do some other things with reference angles. It's very important. Okay, so an example. Let's find alpha, and I'm just going to use that as code for reference angle right now. I'm not going to write out the words. But find alpha if theta is equal to 150 degrees. What you want to do is, there's a step-by-step guide here. Step 1, draw it. Draw theta. So you draw it. And I put the circle in, it's not going to be super important, but there it is. And 150 degrees is a rotation into the second quadrant, so there's the 150. And now what you need to do is to step 2, locate the reference angle position visually. The reference angle here, again, this is a little tricky at first. Sometimes kids get a little confused. They're like, wait, it's an angle somewhere. It's the one that it makes with the x-axis, not the y, the x-axis. And it needs to be positive. It's this angle down here. Now, you might be a little confused about this and say, what do you mean positive? That's not a positive angle. It's like in the second quadrant or something. I'm not thinking of this red angle right now as being in standard position. It's not. In fact, here's a sort of annoying little thing. I'm treating this angle as an old-fashioned angle that's not in standard position, and I'm just measuring how big it is. This one doesn't have a terminal and a terminal ray and an initial ray. It's just this little angle, and it's going to be, obviously, 30 degrees big. It's not going to be negative. It's never going to be negative. It's just going to be a positive acute angle. Acute means between 0 and 90. So it's a 30-degree angle. And so step 3, it sounds kind of silly, but I'm just going to say, use geometry to give the value of alpha. And in this case, alpha is equal to 30 degrees. That's it. So that's the answer. The reference angle for a 150-degree angle is 30 degrees. And I'm just going to say as a final note to this, the sine of 150 can now be calculated. You can actually do the sine of 150 now in your head? Because the sine of 150 is equal to either the sine of 30 or the negative sine of 30. Because of this note we just wrote. Remember, reference angles tell you that you're going to have exactly the same value. 30-degree angle over here is going to have the exact same reference angle as this one, so they're going to have the same sine value. It's either going to be positive or it's going to be negative. Now you might wonder, okay, which is it? Well, you can judge from the picture. Is a 30-degree angle going to have the same sine value as this 151 or different? The opposite. It's going to be positive. It's going to be the same because they're both positive y values. It's going to be a positive sine of 30, and that is equal to 1/2 when you look at the diagram from the last video. Just look at the y value on there, and so the sine of 150 is equal to 1/2. Okay. We're going to do more with reference angles on the next video. Keep thinking about these things because they're really important.